Here's a quick finish of something I didn't realize I didn't say very explicitly at the end of the last video for handout 7. What we really want is that if f and g are two functions and we consider them equal as distributions, and we'll clarify that, then they're equal as functions. And there's one big caveat, which is this is just not really true, because I know I can redefine f and g on at least single points and maybe a countable set, maybe a bigger set, and that has to be clarified. But for right now, we're going to assume f and g are continuous, or at least piecewise continuous, and we don't care about their values at the breakpoints. Okay, but it's simpler if we say continuous. And then what does it mean? What does this mean with the quotes, the little scare quotes? It means that they act in the same way on test functions for all test functions, and of course we have a name for that. D prime is the space of test functions. Okay, or sorry, D is the space of test functions. D prime is the space of distributions, gadgets that act on test functions. Okay, so the thing I just didn't do explicitly, and it's a very, very, very common step with linear algebra, is that I know what happens. I know what kinds of functions get killed when I think of them as distributions, namely only the zero function, as long as we are assuming just continuous functions. And that immediately tells us that if we just put everything on one side, that's zero. That means f minus g equals zero as a function. In other words, is identically zero, and so f and g are identically equal. That's what we really wanted. It wasn't so much that we were interested in the zero function. It really gives us this statement almost for free, based on just a very, very basic linearity principle. Okay, so that's what I really should have finished up with the last video in handout 7, and really says that distributions are generalized functions. Now, how generalized is going to be a very interesting issue, and it's going to cause us some real real thought in a few videos. Okay, so now I want to go to handout 8, and that's about distributions and convolutions, and derivatives are of course going to have to come in because that's what we're using distributions for. That's why they're invented, is they work well with derivatives. Okay, so we've really got a sort of a triangle of concepts, and we want to figure out how they all relate to each other. These guys, we pretty much know. These were invented to make these nice. We definitely need to know how these work together. It's just a little calculus exercise, although we'll put more on our to-do list because it's not an absolutely standard calculus exercise from like BC calculus. And then we're going to need to define this based on how everything else works. Okay. So, so remember where we were way back when in the first. Well, let me say one more thing. This is a redo of an earlier version of the video where I said much more about support conditions, and I'll let you look in the PDF a little bit more about why I'm gonna skip that for now. It's that there's a lot of conditions about improper integrals, minus infinity to infinity, dot, dot, dot. And we're going to do things like take derivatives of those guys with respect to a parameter. We're going to do Fubini switches on these guys. All of those, if you have very general improper integrals that sort of only barely converge, they can be very tricky, and some of the theorems you'd like to be true are just plain wrong without those hypotheses. But it's mostly a technical issue of, do things die at infinity, or do they decay quickly at infinity enough to make all these things work? And it's any technical issue eventually becomes deeper and deeper and more important as you go into analysis. And I'm gonna postpone that for a little bit more. Okay. At the end of the handout, I do bring up a place where supports and whether things go off to infinity or not actually really connects to a very deep issue in physics. But I'm going to kind of bracket that off, put it on our to-do list. And what I'm going to be saying throughout, as you'll notice in the PDF and in the solutions and in what I'm doing with the videos, I'm just going to basically assume, I'm just going to put a blanket assumption in all of the statements that we do, assume that we have, what is it, appropriate vanishing at infinity. And the simplest way to guarantee that is if I have a function that's compactly supported. For those guys, even if you say I'm doing an improper integral, we already know that's not really an improper integral. It's just going from like minus m to m or something like that. And I don't want to do the details of that in each proof yet. Okay. And really, what you really need is just something where it vanishes fast enough and not just kind of barely vanishing at infinity. Okay. So we'll see how that works as we go. But I wanted to mention that I am pushing some stuff off into the to-do list here. Okay, but I don't want to spend a lot of time on it. So now let's look at where we were. I want to go back. I want to keep going back to our major motivations, solving a concrete problem. And here's where we were. If we were able to solve like a mass spring or RLC circuit problem with a delta function, and to be explicit, let's say it's the version where nothing was happening a long time ago. Okay. We have that, and we want to solve for some unknown y. So we're assuming u is known, and we really do know the answer to that problem. But now we're going to put in a fairly arbitrary f, and I want the answer to the same problem, again, with nothing happening in the far past. Okay? Then the claim was very simple. It was that we convolve the hammer blow solution with the given forcing. It's beautiful, beautiful use of convolutions and a little bit of distributions. Okay, and that's Duhamel's principle. Well, he wouldn't have stated it with distributions. Okay, so let's see why that would be true. We finally have the tools to prove it after developing some stuff about convolutions and distributions. And I don't want to just jump in unmotivated to some of the crucial formulas. I want to go back and remind us of how we were kind of working toward that before. Here's what we had, what we were actually pretty sure of. Okay, here's an expression that goes way back. So y naught delta t, and if this is not super familiar, you might want to go back and look at that PDF from ways back. This was something where we took our forcing function, and instead of trying to deal with it as an actual continuous function, we just sampled it at regular intervals delta t, and then converted it to rectangular pulses. Basically as if we were trying to do a Riemann sum of that function. And then we did calculate exactly what the response to the y response to a delta t long pulse, rectangular pulse of forcing at time 0. And what we got was very important. It's a bunch of numbers. These are just numbers. They're not functions of t, times translated versions of a single function y naught delta t. And then times delta t, but I could combine that with that. That's just a number. Okay. So the basic form here, and then what we realized is this looks like a Riemann sum for something that we invented, which was the convolution of two functions. Okay. So the form here is, let me just abstract it a little bit. Let's say I'm taking any function, and I'll do a sum on it, and I'll explain a little bit more about how I want to think about that s. I'm just going to take a bunch of coefficients, ck, just a bunch of random real numbers, which are the generalizations of these numbers here, times translates of the function by some, they don't have to be regularly spaced or anything, some times tau k. So it's a sum of translates of f. And it's really a discretized version. And for us, it was really the thing that predated the convolution for us. But it's a discretized version of the convolution. Okay, that when we look at the expression for the convolution, f star g of t, it's an integral, which is really an overgrown sum, of a bunch of translates of the function f with some weightings that depend on exactly how much you translate it. Now, here you can translate it by any arbitrary real number, and I take kind of a continuous sum to get those all together. But it's really discretizes to this kind of form. And this just makes some of the issues clearer. Okay, so this is an alternate way of thinking of the convolution. If you think of it, and we've thought about it as a weighted moving average, this is just another way of thinking about it. If you think of it as a sum of translates of f, weighted by g, as usual, it's another way to think about that, the role of the weighting function. It's a really good way to think about it, in particular, when you want to think about how derivatives work with convolutions, because that's the first part of our triangle of relationships that we want to do. Let me make it a little bit slicker. We don't even have to mention t here. Just want to remind you that we have a notation for this. There was this notation, that's a ta, of translating a function. When we think about functions, we want to more and more think of them as objects in themselves and things that we don't want to have to always put in an explicit input variable, even though that's, when we get down to cases, that's how functions are defined. Okay, so remember that was a notation for the translation of the function. It's just the same graph as f, just shifted to the right by a. And so that's a way to express it. Just sum coefficients of translates of f. And that's we're going to just abbreviate that very temporarily as SF. It's a very temporary notation because we're going to get back to the actual convolution version pretty soon. Okay. So, oops, I don't know if I should have erased any of that, but okay. So now here's finally, I think we're ready for problem 1. Okay. So I really am interested, and I'll do a slightly quicker version of problem 1. You can work through it slower in the PDF. I really want to know what happens if I take the derivative of this discretized convolution. And it combines two of our most important principles, linearity and symmetry. So this is the derivative of the sum of some coefficients, so a linear combination of derivatives. Okay, and let me go ahead and put in the t, and so this is just f of t minus tau k. Well, the derivative of the sum is the sum of the derivatives, and the constants come out. That's huge. That's a linearity principle. The linearity of the derivative. Now, the derivative of f translated, it's a super easy application of the chain rule. It's just take the derivative first and then translate. And it's, even though it's the world's easiest application of the chain rule, it's still really deep. It says that the derivative, if you take the derivative of a function, there's nothing special about taking like f prime at minus 3. Okay? If I take this function and I slide it over so that that feature is over here at plus 3 and I take its derivative, I'm going to get the same answer. And there's nothing special about, oh wait, I'm taking a derivative at 3. There's something weird about that point fundamentally on the line. I do something different. I always take the slope of the tangent line. That's what really is happening when you do this application of the chain rule. So it's actually a symmetry principle. So, in other words, that's just what the S operation, the sum of a particular linear combination of particular translates, applied to f prime. Okay, so that's really, really easy and using fundamental principles, and it gives us a really good hint as to what. So this is number, as 1C, I guess. Okay, so f star g is supposed to be the continuous analog of SF, and so this seems to say, okay, nothing happened to the coefficients. The CK's didn't change, the tau k's didn't change, so the weighting doesn't change, and the only thing that happened is you could either do the sum of the weighted sum of translates of f and then take the derivative, or take the derivative and then take the weighted sum of translates. Okay, so that's what we really expect to get. And the rest really is sort of technicalities. But we can actually even, before we just grind into a calculation, and I hope I'm not setting it up to be a really intimidating calculation, it's not, but it does bring in a bit of calculus that most people don't see the first time they take it. So here's what we could also observe, if this is true, okay, if f star g prime is f prime star g, well, this is a great thing to do in mathematics is before you prove something, especially if you think you don't know how to prove it, think about some consequences, think about things that are equivalent to it, get some more evidence and get a circle of ideas around it. Okay, we can use the symmetry here. This is g star f, okay, prime. Okay, it looks like we're saying that's going to be g prime star f. We had this argument that we can pull the prime into the left-hand side. There shouldn't be anything special about the left-hand side. Oh yeah, that's f star g prime. Okay, so in particular, these should be equal. If this guy is really equal to this, then these should be equal, and that's not 100% obvious. It looks like a symmetry principle, but it's not completely obvious that that's how it works. 'Cause I'm not just literally switching the g and the f prime, okay? I'm putting the prime in a different location. Okay, so, and it turns out we can check that slightly in a slightly different way, and I think slightly easier standard sort of calculus argument than checking this guy. So we'll leave that for just one sec, and then we'll do this. Okay, so let's look at that. And here's going to be one of those places where I play fast and loose with um, improper integrals, and you'll see what I meant about that. Okay, f prime star g of t. Oops, I think I have a ta in the. Yeah, it should be of t. I don't know if that's worth correcting and reloading. Okay, so that is f prime. You know what? Actually, it's just slightly easier if I start with that. We'll see where to go better. And a certain sign will just be slightly easier. So we'll start from that, because I happen to know it works. Okay, so there's just the definition. Okay, and then anytime you have a product and there's a derivative on one of the factors, oh my god, we got to do integration by parts. Okay, so this is going to be f of t minus tau g of tau evaluated from tau equals minus infinity to tau equals infinity. Those are really limits, of course. You take the limit as some finite version of tau goes to minus infinity or infinity. And then minus the derivative with respect to tau of f of t minus tau. Let's see if I can fit it, just barely. G of tau d tau. Okay. Okay, there we go. All right, so now here is where I'm just going to kind of play fast and loose with this. You have to be slightly careful to just say that can die. That's going to die. But if either f and g are dying really fast at infinity, or even decently fast at infinity, or if they're compactly supported, or if actually just one of them is compactly supported, it turns out that that's no problem at all. And then I just have a little chain rule thing. This is the slightly less trivial case of the chain rule. There's a minus in front of the tau there. That actually canceled that minus nicely. And we do get, with a plus sign, miracle of miracles, just f prime applied to t minus tau, g of tau d tau. Because notice here, I take f and modify it. I take t of t minus tau, not just of t or of tau, and then take the derivative. This says take the derivative first and then put in t minus tau. And there is a minus sign from the chain rule. But luckily it canceled, well, not luck, but it has to cancel that minus, or else this whole story doesn't work out. Okay, and so of course that's f prime star g applied to evaluated at t. Okay, so in other words, integration by parts. That's the 2-second explanation. That works because of integration by parts. Now the other one though is a little more interesting calculus statement. Okay, so now we're actually going to get to it. We've kind of danced around it a little bit. We'll do this, and then that'll be plenty to stop with. Okay, because I know it's getting like 20 minutes long. But hey, I've started with another handout, and I'm doing this handout. Okay, so that's d by dt. You know, let me be a little careful about how to write this. Let me actually have a name for where I'm going to calculate it and make it different from t. That's this thing about this notation is you can confuse a variable with a value of the variable. So that's what this is for. Okay. Okay, so that's going to be, just write down the definition. Okay. Now here's what we're doing. We're taking the derivative of an overgrown sum, a sum in the tau variable, but then it becomes the tau is a dummy variable. When it sums out, the actual variable that survives is t, and we're familiar with that from doing a bunch of convolutions. And then you can take the derivative with respect to t. Well, the derivative of a sum should be the sum of the derivatives, so I should be able to pass this in. Now, the reason that's not just obvious and trivial to prove is that the overgrown part is there's a limit involved, and especially the limit as you do an improper integral, that can be a fairly finicky limit if f and g are not super well behaved. Now again, if either one of these is compactly supported, it's not hard to show that this guy collapses to a finite integral. You still have to prove, there's still an implicit limit in there, a limit of Riemann sums. You still have to prove this, that you can pass the derivative inside. But morally, it's something you should expect with some technical hypotheses based on the derivative of a sum is the sum of the derivatives. Oh, however, I need to be careful about this. This should be a partial derivative. This guy is a function of two variables here, and the dummy variable has not gone away yet, and I have no business taking a derivative with respect to tau. It really is just should be the partial derivative. So again, there's a subtlety here, but this is a true fact with proper assumptions. It's going to be it's on our to-do list to really prove this exact fact. Okay, and now it's easy because this guy doesn't depend on t. This guy, it's again the super simplest, easy case of the chain rule. You might want to compare this to the argument with S, because it maps step for step to the argument with S. This is f prime of t minus tau, g of tau d tau. Hey, that is exactly f prime star g of, ooh, and this is at t naught. Now I actually evaluate it at t naught, and that's at t naught. So this really is true, and this one's pretty long, so we'll stop here and resume in the next video.